I'm going to review Cohen's D for a one sample t-test first, and then we'll go on to the independent and dependent effect sizes. So Cohen's D is an effect size for means. Another type of effect size is correlations, or R's, but we're going to focus on Cohen's D here. The effect size is a measure of the practical significance of a hypothesis test. So if we find a hypothesis test to be statistically significant, then you should also see if it's practically significant. So what that means is that you could have a really high powered test. Say you have a really high sample size, and so your test is really powered. And it'll find any difference that there is, even if it's really small, because you have so much power. You might want to see if you really care about this difference, a significant difference. So I've been giving an example of pizza delivery times, and if you find a significant difference from, say, 30 minutes for the average, that's great, but is that really a practically significant result? So if it's a half a minute, so for delivery times in the average, that's probably something you don't really care about. So if you want to make sure that the average time for the pizza deliveries is not greater than 30 minutes and you find a sample average of 30.5, you're probably not going to care too much about that. You could find it to be statistically significant if you have enough power, but half a minute's not something you really care about. But if it's 10 minutes and you find a difference of 10 minutes and the average delivery time in your study is 40 minutes and they claim to be 30 minutes or less, then yeah, you might care about that. Or you'd care even more so if it was 50 minutes. So that's what I mean by practical significance, is do we really care about the difference that we find? And when we talk about minutes, it's a little easier to see if that difference is practically significant because the outcome measure is something concrete, it's minutes. But if you have something that is not so concrete, it's abstract, like you fill out a personality inventory, or you have the people in your study fill out personality inventory, and you want to see if they differ from a certain value in conscientiousness, then the effect size there is going to be a little more ambiguous. So calculating Cohen's D for something like a personality inventory is pretty important. If the outcome measure is more concrete, like minutes, then it's not as important, but you can still do it. And you can see for a one sample mean test here that to get Cohen's D, you do the sample mean minus your comparison value that you had in the null. So whatever you think is important, whatever value you think is important, we call that usually the comparison value. And in the pizza example would be 30. And then you divide by the standard deviation and not the standard error, because the standard error is really affected by how much power you have in your test. It's affected by the sample size, which affects your power. So we don't want to know if it's statistically significant. We already determined that with the hypothesis test. We want to know if it's practically significant. So we just divide it by the standard deviation. So this is how much you expect them to kind of vary in the population. Now we're going to go over Cohen's D for an independent design. So we're doing an independent t-test, and say you find a significant result. You want to know, is this practically significant? So in this formula here for Cohen's D, we're going to assume equal population standard deviations. And there's a different formula if you don't assume this. So the sample standard deviations are going to vary just by chance, even if the population standard deviations are equal to each other. So first you need to decide if you want to assume that the population standard deviations are equal or not. And for this class, we're always going to assume that. And then the D is calculated as such. It's the difference in the sample means minus 0 divided by the pooled standard deviation. So this looks very similar to the one sample D. The basic formula is the same. So on the bottom of both, we have standard deviation. It's just in this one, we have the pooled standard deviation because we have two separate standard deviations, one for the first sample and one for the second sample, and then we make a weighted average of them, and this is called the pooled standard deviation. And the pooled standard deviation, as I said, was a weighted average of the two standard deviations, and it gives more weight to the sample with a higher sample size because we assume that has more information. And we give less weight to the sample with a lower sample size. So that's the bottom of the pooled standard standard deviation here. And then the bottom here, on the top, we have the difference between the sample means. Normally we just have one sample mean here for the one sample example, but now we're comparing two means, so we have two means here and we find the difference. And then here we're subtracting off 0, which seems a lot different than the one sample Cohen's D, but it's really not, because before we were subtracting off the number and the null, and we're doing the same thing here. It just happens that the number and the null is 0. And you can pick something besides 0 if you want. If you do the same thing in your hypothesis test, don't just do it for fun, but if you have a reason to do it. But if we set the number and the null to be 0, that means that the null is saying that there's no difference between the population means. So if you subtract the population means and get 0, that means there's no difference. So that's why we're putting a 0 here. Now you can pick something else if you wanted to, if there was a reason to have the null difference as 1 or 2 or whatever number. If there was a reason for it, normally almost like 99% of the time we put 0 here. And always for this class we will put 0. So don't worry about it too much. I just want you to know why we have a minus 0 here when subtracting 0 really doesn't change the Cohens D. And then the Cohens D for dependent designs is a little bit more complicated. So if you go directly off the one sample example, you would probably get something like the first D. And this is called DZ. And to get DZ, Z refers to the difference scores. Then you want to get the sample mean of the difference scores minus 0 divided by the standard deviation of the difference scores. So this almost looks like a one sample D. We subtract 0 because that's the null comparison value. If the average of the difference scores is 0, then that means there was no difference between the pre and the post test, or twin 1 and twin 2, or whatever pairing that you have. So that's why we have 0 there. So it almost looks like a one sample test. The Cohens D for a one sample test, so we just have 0 as our null comparison value. When we do this, though, the standard deviation is usually kind of small, on the smaller side, because the individual differences are removed. So we have less noise going on, and our standard deviation is smaller, which is great. But what happens is our effect size might look really big when you compare it to an independent design. And that's because the standard deviation in an independent design doesn't have the individual differences removed. And removing the individual differences helps us have a more powerful test, but it doesn't really make that difference that we find any more practically significant. So removing the individual differences helps our power, helps us find a statistically significant result, but it doesn't really help the practical significance. So if you're doing a power analysis, DZ is good. And that's what you would have to use if you're calculating the sample size needed to achieve a certain amount of power. So you'd use DZ. If instead you wanted to know the practical significance, if you want to know, okay, yeah, it's statistically significant, but is this really any use to me? Then you want to do this second formula, which is DAV, which means Cohen's D average, basically, referring to averaging the standard deviations. So the top looks the same. It's the average of the difference scores minus 0, or whatever comparison value you had in your hypothesis test. And then you're going to divide by the average of the standard deviations. So you're going to get the standard deviation for time 1 and the standard deviation for time 2 and divide by 2 if you have a repeated measure design, meaning the same person is taking the test twice. Or if you have two twins, then you can get the standard deviation for twin 1 plus the standard deviation for twin 2 and divide by 2. Whatever you're pairing by. So it's kind of like the independent design Cohen's D, because we're weighting the standard deviations. We just happen to have the same sample size in time 1 and time 2, right? Because you have the same amount of people in each. And so we weight the standard deviations equally. So it's very comparable to the independent design. So if you want to know, hey, is this practically significant, then use DAV. If you need to use the Cohen's D for power analysis, use DZ.